Okay, next idea we're going to talk about involves this object called a relation among a list of vectors. And here's what it is. A relation is a list of coefficients. That's a very specific and special list of coefficients. It's a list of coefficients such that when you take a linear combination with those coefficients of your original vectors, you must get 0. So a relation is a demonstration of the fact that you can take a linear combination of your given list of vectors and arrive at the result 0. Now, why do we call that a relation? Well, it shows a sort of a relationship between these vectors. In some sense, this is unexpected. These vectors here, if they're not all the 0 vector or something like that, they're perhaps pointing in every different direction, who knows where, and the idea that you can take some linear combination of them and have it add up to 0, it's not clear that that's even possible. So if it is possible, it shows some sort of a relationship between these vectors and thus reasonable motivation for this term relation. Now, do notice that a relation is a list of coefficients. It's this list of numbers. And you can think of that relation, therefore, as being a vector. Okay. We'll talk more about that later. A little bit of terminology. If those coefficients here are all zeros, well, that's not a very impressive observation. We're going to call that the trivial relation because, of course, if you multiply all these vectors by 0, you get a bunch of zeros which you then add up. Well, then, of course, you do get 0. So no matter what vectors you're looking at, of course, this relation will work. And the fact that it's always true means it's never interesting, and so we call it the trivial relation. Okay. All right. We're going to find ourselves needing to make reference to non-trivial relations, and to avoid the negative, just to have the lingo be a little bit more natural, we're going to call those significant relations. Okay. So every relation is either a trivial relation or a significant relation. Okay. So with that definition in mind, here's our definition of the next big important idea. We say that a list of vectors is linearly dependent if they have a significant relation. So, in other words, there needs to be a way let's color code, there needs to be a relation, namely a list of coefficients that makes this linear combination add up to 0, but importantly, it needs to be a significant relation. So these numbers can't all be 0. Again, if your relation consists of all zeros, then this is not a very impressive observation. And certainly it doesn't say anything interesting about the vectors, because that algebra would always be true if those coefficients were allowed to be 0. Okay, always true, never interesting. All right, so this is our definition of what it means for a list of vectors to be linearly dependent. They have something to do with each other, they depend on each other because there is a relationship between them. Okay. All right. So you can probably guess our definition of what it means for a list of vectors to be linearly independent. Well, independent means not dependent. Said differently, there is no significant relation. And if there's no significant relation, another way to say that is that the only relation is the trivial relation. Okay. All right. So in other words, the only way to make a linear combination to add up to 0, the only relation is if those coefficients are all 0. Namely, the only relation is the trivial relation. Okay. All right, now I'm going to write down quickly a rewrite, an alternative formulation of linear independence, and that is that there is no significant relation. Again, this is directly the opposite of saying that there is a significant relation. So this is a very natural point of view on linear independence. This is no significant relation. And you see now one of the motivations for this term significant, because if instead we were to say no non-trivial relation, then we have this awkwardness of a kind of a double negative. Saying that there is no non-trivial relation, it's easy to get lost amongst the negatives. So replacing this word non-trivial with significant is nice. Okay. All right. Important feature to keep in mind of these notions of independence and dependence is that we're talking about properties of a list of vectors. We are not talking about the individual vectors in the list. So very importantly, if you have a list of vectors v1 through vn, that list of vectors may be dependent. That list of vectors may be independent. In either case, you would say that the list is, whichever it is. It's either it is dependent or it is independent. The trouble is, this list consists of a bunch of individual vectors, and when you're talking about this, it's very easy to say v1, comma, through vn, and to think of this as being a plural, and to inadvertently say are, to say that these vectors are dependent or independent. Well, saying are in that place would suggest that we're talking about properties of the individual vectors. And we're not. We're not talking about a property of v1. I'm not saying that v1 is dependent, and furthermore v2 is dependent, etc., and furthermore vn, and therefore all individually these vectors are dependent. That's absolutely not what we're talking about. We're talking about the list as a whole, which is importantly singular, and therefore importantly is dependent or independent. It's easy to mess this up. In fact, this is super common. It is so common that it's really not a problem. Once you're very thoroughly comfortable with what this idea is, that linear independence is a property of a list of vectors, then everyone knows what you mean. So outside of the context of Math216, be aware that you're going to hear people say are. These vectors are dependent or independent. In fact, I'm sure I will commit that mistake myself. But it's important that you as students are careful about this, because you need to demonstrate that you understand that we're talking about a property of a list and that we're not talking about a property of individual vectors. So try to be as careful as you can with the grammar. Okay, so here's some examples. What does linear dependence look like? Now you'll notice I'm going to talk about dependence. Keep in mind, dependence, collection of vectors, is dependent if there is a significant relation. So what I'm going to draw here are pictures of lists of vectors that have a relation. So here's one. This pair of vectors here, v and w, there is a relation amongst those vectors. That is, if I were to multiply this by just the right amount, I would get the other vector, which if I then multiplied by -1, add them up, you get 0. Right? So that would be a significant relation between these two vectors. Therefore, this list is dependent. Okay. Likewise, this list, this trio of vectors, is dependent because a certain multiple of this minus that would give me 0. Okay. So you'll notice in both of these cases the dependence that we observe, the relations that we observe, are based on the fact that one of the vectors is a multiple of one of the other vectors. Okay. All right. But there are other ways in which a list can be dependent. So here we have a trio of vectors. There's v, there's w, but then there's also the 0 vector. And that trio is dependent. And geometrically, it's not immediately clear that this list is dependent, but if you think through, linear combinations here, if I were to write down 1 times the 0 vector plus 0 times v plus 0 times w, notice that what I have is a linear combination of these vectors 0, v, and w. And those coefficients, some of them are 0, but they are not all 0. This is a significant relation because that one is not 0. So this list of vectors here is dependent. In fact, this is true for any list of vectors that contains the 0 vector, dependent by a similar argument. Okay. Here's another example. Suppose one of the vectors is a linear combination of the others. Well, then again, this is not hard to see how the relation would be constructed. If that vector, w, is a linear combination of the others, then that appropriate linear combination of the other vectors minus w would give you 0. Okay, so a significant relation. Now, what if you have a trio of vectors specifically in R2? And now, importantly, this is just in R2. Right? A trio of vectors. 1, 2, 3. That trio of vectors in R2. There's temptation to say, well, gosh, that trio of vectors has got to be dependent because, well, it just feels like there's not enough room to have these 3 vectors point in not only all different directions, but in directions that can't be forced to relate to each other. And so you can try different ways, for example, to avoid this. One thing you could do, for example, is, now the way I have them drawn here, it's clear that that one is a linear combination of these 2. But what if I were to throw away these vectors and say, well, okay, well, yeah, in that case, sure. But what if I have that vector and that vector and that vector? Well, now this one is not a linear combination of those 2. Doesn't that contradict our assertion? Well, the thing is, we're not obligated for this vector to be a linear combination of these 2. In this case, the whole effort to try to make that happen, to make this one not a linear combination of the other 2, makes this one a multiple of that one. And thus we have a relation. So trying to avoid this vector being involved in a relation forces these vectors to be involved in a relation. So you can twist and turn and try to figure out different ways that you can draw 3 vectors in R2 such that there's no relation, no significant relation between them, and you will never be able to make that work. So I'm going to say here that a trio of vectors in R2 is dependent. I'm going to leave this question, are we sure about this? Our personal failure to come up with a counterexample, our personal failure to develop an intuition for how to construct such an example doesn't mean that there isn't one out there. It just means that we haven't thought of it. Right, so we have to worry about this. How do we know that such a list is dependent? We'll come back and talk about that in a moment. Similarly, a little bit more geometrically challenging, but if you have 4 vectors in R3, such a list of 4 vectors will always be dependent. And again, looming question, how do we know? Certainly we're going to fail to come up with an independent list of 4 vectors. No matter how we write 4 vectors, it's going to be, there will be a relation between them, a significant relation between them. But how do we know? Okay, come back and talk about that as well. All right, we're going to start with an easier example, and that is to consider a pair of vectors in R2. Let's ask the question, dependent or independent? Going back to our definition, remember that it goes to the relations. is there a significant relation, or is the trivial relation the only relation? Right? One way or the other, we're looking for relations. And relations are described by linear combinations that add up to 0. Okay, so that's what we're going to look at here. We're going to take this pair of vectors. We're trying to decide if they're, oh gosh, I just did it. I just said if these vectors are. We're trying to decide if this list of vectors is independent or dependent. So we're going to look at linear combinations of those vectors that add up to 0, and we're going to ask, what can we conclude about these numbers here? Can I conclude that only the trivial relation works? Or maybe might I be able to find some non-trivial relation? Okay. Well, again, interestingly, note that we have a vector equation. Looking one coordinate at a time, that gives us a system of equations, which of course I can write as a matrix equation. So this question about independence or dependence again boils down to a system of equations. And what can I conclude about this system of equations? Now, keep in mind our goal is to decide if there's a significant relation or if it's only the trivial relation. In other words, my goal is to ask, is 0 the only solution? Another way to say that is, and by the way, of course, I can see that 0 is clearly a solution. It's clearly going to make the system works. So another way to phrase this is, does this system of equation have a unique solution, that unique solution clearly being 0, or does it have multiple solutions? So this boils down to a question of uniqueness. And I need to decide if this matrix does or does not have the uniqueness property. Does this matrix have the uniqueness properties? Well, one thing you could do is take this matrix and row reduce and see, is there or is there not a pivot in every column? And you could certainly do that. It's not a hard row reduction. Much more convenient than that, though, is to compute the determinant. Observe that it's not 0. Cite facts about determinant. In particular, that means that this matrix is non-singular, and therefore we have the desired uniqueness property. Therefore, the only relation is the trivial relation, and that means that the list is independent. So we do get a result from looking at this algebra. And interestingly, notice that just like the span question boils down to a system of equations, namely it boils down to looking at a matrix. With the span question, we were interested in whether that matrix has the existence property. And here with the independence question, we were interested in whether this matrix has the uniqueness property. It's interesting that these independence and span at a glance don't appear to be directly related, but the algebra that addresses them is very closely related. Okay, we'll see much more about that as time goes on. So this approach to asking if a list of vectors is independent or dependent, breaking it down to a matrix, will allow you to answer these questions. This will be a wonderful little exercise for you guys to work out on your own. Write down what that matrix would look like in this case of 3 vectors in R2, of 4 vectors in R3, and you will get matrices of a particular shape. And the shape of those matrices will allow you to answer these questions as required. So give that a try. It'd be a nice exercise. And of course, if you have any questions, feel free to ask in office hours to get clarification.